The final chapter that we are going to study in AP Physics is Chapter 23, Circuits. And so this is a good time to sort of go back and tie together some of the information we've learned from Chapters 20 and 21 and where we are right now in Chapter 22. So where are we at right now? Well, first we know that electric charges exert an electric force on each other given by this equation, in which K is the constant you see here. And there are two charges. We put them in absolute value because we only care about their magnitude, not about their sign. And the distance between them squared is on the bottom of the equation. We also know that the electric force is directly related to the magnitude of the charges. Let's look at some examples. For example, if I double one of the charges, well, that'll double the electric force. However, if I double both charges, then that is 2 times 2, or 4 times the electric force. Likewise, if I cut a charge in half, that cuts the force in half. If I cut them both in half, it cuts the force by 1/4. The electric force is also inversely related to the square of the distance. For example, if I double the distance, well, 2 squared is 4, but the inverse is 1/4, so the electric force is 1/4. However, if I cut the distance between them in half, 1/2 squared is 1/4, and the inverse of that is 4, so the electric force is multiplied by 4. Make sure you understand those. We also know that electric forces are like other forces. In other words, they can be added together. Of course, sometimes that means that you actually add them if they're going in the same direction, and sometimes you subtract the vectors if they're going in different directions. Electric forces are like vectors, so if I have a force directed at an angle theta, I can find the horizontal and vertical components of that force by using trigonometry. Likewise, if I need to add a horizontal and a vertical force together, I can do so using the Pythagorean theorem and the inverse tangent. Although electric fields are not stressed in AP1, we have seen that an electric charge will put out an electric field around it. When a small positive test charge is placed in this electric field, the electric force pushes it away. The equation for the electric field is the electric force divided by the test charge. And this is a force per unit charge. This equation is equal to K Q1 over R squared. Notice the Q2 has just been moved to the bottom of the equation on the other side. Let's check what we've seen so far. Another important concept to understand is electric potential. But to discuss electric potential, let us first look at gravitational potential. Here I have a 2 kilogram kitten, a 4 kilogram goat, and an 8 kilogram grasshopper. Right now they have 0 gravitational potential energy. But if I were to raise them 10 meters up in the air, they would suddenly have the potential to have gravitational potential energy. As you know, gravitational potential energy is given by the equation U sub g equals mgh. I've put the gh in parentheses for a reason which will become evident soon. So if we look at the data here, we see that each of the masses get multiplied by the same gh, which in this case is 98, and we can find the gravitational potential energy for each of them. Now if we divide each of their gravitational potential energies by their masses, we will get the same number, 98. It is this number that any mass would be multiplied by to find the gravitational potential energy. So we have the gravitational potential energy given by the equation mgh, and that is specific for each of the different animals. But we also have something called the gravitational potential, and that is just the value of gravity times the specific height at which you are measuring from. And that will be the same no matter what animal is very carefully dropped from that cliff. Understanding the difference between the gravitational potential energy and gravitational potential will help you to better understand electric potential. Here we have a bunch of charges that are all collected in one plate. This is like the animals that were all on the ground. There is no potential energy for these charges. However, if I separate the two plates with all the negatives on one side and all the positives on the other, we have a parallel plate capacitor. And now the charges at least have the potential to get potential energy, just like the animals did when they were sitting on top of the cliff. However, the animals had a path to the bottom through the air. These negative and positive charges have no path to get from one plate to the other. So we need to add a path by adding a wire in from one of the plates to the other plate. Once we have connected the wire, the electrons begin to flow from the negative plate to the positive plate where they neutralize a positive charge. Notice that the electrons flow in this direction. However, current flow is considered to be from positive to negative, as if their positive charges were moving through the wire instead. Once all of the charges have been used in the parallel plate capacitor, there is no longer any current. If we connect the two plates and have certain chemicals between them, like you might find in a battery, now as the charge moves through the current and reaches the other plate, it reacts with the chemicals, and the negative charges and positive charges are no longer neutralized, but instead are moved to their corresponding plate, so the process can happen once again. Before, we had our gravitational potential energy was equal to mgh. Now we have an electric potential energy, which is equal to the charge times V, which is the voltage. Likewise, before we divided our gravitational potential energy by the mass to get something called the gravitational potential. Now we can do the same by dividing the electric potential energy by the charge, and that shows that V equals the voltage, and this is called electric potential. This electric potential, measured in volts, will come back again in just a little bit. One last reminder. Although it is the negatively charged electrons that are able to flow through the metal, current flow is considered to move in the opposite direction, as if the positive charges were moving. Let's check our understanding about what we've learned about currents so far. So when we connect a parallel plate capacitor with a wire, several things can happen that indicates a current is moving. The wire can get warm as the electrons that are moving through bang against each other and have atomic friction. A thin filament that's in a light bulb could heat up and therefore glow, giving us light, and a compass needle can be deflected. All of these are proof that a current is occurring through a wire. Your book gives a great analogy of water moving through a pipe and the flow of electrons moving through a wire. Now, just as water wouldn't be used up as it spins a turbine going through a pipe, electrons aren't used up just because they are causing a light bulb to light, or deflecting a needle, or running a toaster. That leads us to the law of conservation of current. The current is the same at all points in a current-carrying wire. I may be overemphasizing this, but we need to remember that current is the flow of the positive charge, even though the positive charges don't flow. It's the electrons that flow through a wire. Now keep this in mind as we look at the next diagrams, which will show the positive charges moving. Now current is due to the motion of the charges, and so we can define current as the rate of motion of charges through an electric field. In other words, how many charges pass a given point in a given amount of time. The equation for current is I equals delta Q over delta T, where I stands for the current. Now if the charge Q is measured in coulombs and time is measured in seconds, then current is measured in coulombs per seconds. 1 coulomb per second is equal to 1 ampere, or 1 amp, and here you see the abbreviation for ampere. Another way to look at this equation is to rewrite it in terms of Q, and here we see that Q, the total amount of charge, can be found by multiplying the current times the time interval. The last thing you read on Friday concerned what happens when a current either enters or exits a junction. Now it just makes sense. If water was coming to this top junction, some would go to the top and some would go to the bottom, but it'd still be the same amount of water. For current, the same thing happens. According to Kirchhoff's junction law, the sum of the currents entering a junction is equal to the sum of the currents exiting a junction. Time for another short review. Yay, we're almost near the end. We just need to talk a little bit more about batteries to make sure that you understand them. Now we have seen that if we separate charges on two plates, we have a capacitor, but we need to connect the two plates with a wire and then provide something in between them, some sort of chemicals, so that the charges can be moved from one plate to another and thus replenish the supply. So here we have an electron moving around the wire to the positive plate, and then it travels through the chemicals to return to the negative side. But what exactly is happening in the battery? Here we see that as the charge flows through the wire and reaches the opposite plate, chemical reactions take place within the battery, which cause positive ions to move to the positive plate, and leave negative ions to collect on the negative plate, and thus the process continue over and over. Now we know that the electric potential energy is equal to the charge times the electric potential, or voltage, much like the gravitational potential energy was equal to mass times gravity and height. We can now say that the flow of charge in a continuous loop is called a complete circuit, and that is where we are headed to in our final chapter. This separation of charges in our battery, putting the positives up on the positive plate and leaving the negatives on the negative, creates a potential difference, much like when we raised our animals up to a taller height, gave them a potential gravitational difference. The potential difference established by something such as a battery is called the EMF. EMF stands for the electromotive force. Its symbol is a capital epsilon, and the units for the EMF are volts. So now we see volts, which was our electric potential, has come back again. A battery's rating, whether it's a 1.5 volt battery or a 9 volt battery, is a measure of its electromotive force. Now, when a battery is hooked up to a circuit, due to some of the chemical processes within the battery, the actual voltage is a little bit less than what it's registered at. But for the purposes for this class, we will say that a 1.5 volt battery actually delivers 1.5 volts. And the same thing for a 9 volt battery or any other battery we talk about. So that's it for this video. We've looked at two of the three parts for describing circuits. We've looked at the electric potential or voltage, and we've looked at the current or the amperes. Next we will look at the resistance.